In this video, we'll be looking at the Hertzsprung-Russell diagram using a simulator published by the University of Nebraska at Lincoln. We'll look at the relationship between luminosity, temperature, and radius in stars, and how we can interpret the position of a star on the Hertzsprung-Russell diagram. The simulator shows how two different stars compare with one another. On the left, you'll see our example star. And then on the right, you'll see the sun, which is there for reference. To start out with, we'll look at a star that's exactly like the sun. On the Hertzsprung-Russell diagram, temperature increases to the left, and luminosity increases up. Now you'll notice, first, that having the x-axis on a graph increase towards the left, that's kind of unusual. And this happens for historical reasons that I'll talk to you about in regular lecture. But for the purposes of this video, we're just running through this simulator and seeing what it can tell us about how to interpret the HR diagram. I'll start by taking my imaginary star, marked by this X right here, and I'll drag that to the left. So we're going to drag it towards higher temperatures. And watch what happens to the example star as I move its position in the temperature axis. So I'm going to try to keep it at constant luminosity, but move it straight left across the diagram. As I do this, you'll see that it's going to move, the X is going to move below those lines of constant radius. Those diagonal lines, those diagonal green lines, are labeled with the size of the star at those positions. So I've now gone from a star equal in radius to the sun to 10 times smaller. So it's only now 1/10 of the radius of the sun. And you see that reflected in the mini window to the left. I've increased the temperature of the star at fixed luminosity. And as we saw in class, there's a connection between total luminosity, radius, and temperature. Increasing either temperature or radius will tend to increase the luminosity of the star. So that is, I have two variables that can control the luminosity, temperature and radius. If I increase temperature, luminosity tends to want to increase. So if I want to keep the luminosity the same, while increasing temperature, I have to decrease the radius. That is, temperature goes up, radius goes down at constant luminosity. And that's what we've just seen. On the other hand, if I keep the temperature the same, but start increasing the luminosity, the only way I can do that is to use that second variable. So I've got those two variables, temperature and radius. But if I keep temperature the same, I lose that variable. The only thing left I have to play with is radius. And so if I want to raise the luminosity, I have to raise the temperature. Or excuse me, I have to raise the radius, keeping the temperature the same. And as I start dragging this X up, as you'll see, once again, I'm moving back towards that one solar mass line of one solar radius line of constant size. And if I keep going, I'm going to go past that. Okay, now I'm back on the main sequence again. And we'll see that the main sequence crosses these lines of constant radius. So at very, very low temperature and low luminosity, there's also small size on that main sequence. Whereas at higher temperatures and higher luminosities, the star gets bigger. But I can even go past that. I can go above the main sequence, say up here, where now I'm between 10 and 100 times the size of the sun, and that gets me into supergiant territory. Now I'm going to pull back on that just a little bit to make my last change a little bit more obvious. So I'll go back down to about 10 times the size of the sun. Now let's imagine doing the reverse of our first step. In that first step, we increase the temperature at constant luminosity. And as a result, the size of the star had to decrease. If I wanted to keep the luminosity the same while raising temperature, I had to decrease radius. Now I'm going to flip that. So I'm going to decrease the temperature, but keep the luminosity the same, and the only way I can get away with that is to increase the radius. So I'll start dragging this star to the right now, and as you'll see, indeed, that star in the inset is getting even larger still. It's now getting so large that I can't even really see its curvature anymore. It looks like it's just going straight up and down, and now it's about 1,000 times the radius of the sun, and you'll notice its color has changed as well. We went from blue over here because it's hot, and hot stars are blue, to sort of reddish orange by the time we get over here, because cool stars have a reddish or orangish color. That's basically what happens as we move around in the AHR diagram. So we can start down here in the lower left corner with very, very small stars. Moving to the right, stars are going to get bigger. So lower left corner, stars are sort of medium sized, kind of comparable to the sun. Moving to the upper left, we get relatively large stars. And then finally, our largest stars are over here in this upper right quadrant of the diagram. We'll call those huge. Stars across the top of this HR diagram, they're so big, we call them supergiant stars. And we'll talk about luminosity classification in another video.